Yeah, so the title of my talk is Regions of Attraction to Limit Cycles of Nonlinear Hybrid Systems. And thanks to the last two talks, I don't really have to go into any detail about what nonlinear hybrid systems are. So, well, hybrid limit cycles are central in dynamic walking. For example, everybody's favorite example that they start with is the compass gate walker. We see here a limit cycle. It's hybrid because of the impacts. It's very nonlinear. So probably most people here know that a limit cycle of an autonomous system cannot be stable cannot be asymptotically stable in the classical sense, because if you start two different initial conditions both on the limit cycle, they'll keep going around the limit cycle but stay kind of the same distance apart. They'll never converge to each other. So there's no asymptotic stability, but there can be orbital stability, which means solutions away from the cycle converge to the cycle geometrically in phase space. So there are existing methods to characterize local orbital stability. For example, Katja was using the Poincaré map, and Anton has used before the transverse linearization. These methods so far characterize just in some region around, or some local property of stability, but without any real definition of how local that is. So it's very interesting, I think, to be able to study regions of attraction as well. So what we have here is a guaranteed region of attraction for the same compass gate walker with a controller which I computed using also transverse linearization techniques. So what I'm saying is, I'm not saying this is absolutely every initial condition that will converge to the cycle, but this is a possibly conservative set which definitely will converge to the cycle. And we'll look at, as I go through with some simpler examples, we'll see where that degree of conservatism might come from. But region of stability analysis like this has traditionally been quite difficult. For some planar systems, there's some qualitative theory which can be used to give some quite strong results. But for anything with more than two states, it's pretty hard. And often you just end up doing exhaustive simulation. So this region of attraction here took, with the methods I'm going to present today, took about 5 minutes to compute, whereas to get something of kind of similar accuracy using exhaustive simulation, saying it took 1 second for each simulation to run until you were sure it was stable, back of the envelope calculations say that would take about 3.5 years of computation. So using some efficient optimization methods can make a big difference. So this is very interesting for analysis of autonomous oscillations, or you might be designing different controllers and choosing one which had the biggest region of attraction. But it's also useful as a component in broader control methods. So for example, Russ has presented the idea of LQR trees, where you're going to stabilize one nominal cycle and then keep reconnecting back to that and keep kind of filling out the state space with these regions of guaranteed convergence. And you're going to use these regions also to influence how you're sampling in the state space to make these reconnecting motions. Bobby Gregg also spoke about composition of motion primitives. So you might want to plan a motion over up and down stairs or over rough terrain by choosing the next motion primitive which does what you want, but checking also that you're in the region of stability for that motion. So being able to efficiently compute these regions for a big class of motion primitives is something very important for that sort of controller. And oh, I should thank Mark Demenken, who did a lot of work computing these examples as well. So there's going to be a few equations in this talk, but the most important equation is this one, which is basically if you take transverse dynamics for nonlinear hybrid systems and add to that regional verification of Lyapunov functions via a sums of squares relaxation, you get region of stability analysis for hybrid limit cycles. So I'm going to step through both of these different things and explain what they mean with the aid of a few simple examples. So I'm going to start with the transverse dynamics. I used to work with Anton Chiryaev, and he taught me all about transverse linearization, and I think it's a really powerful tool for studying these limit cycle behaviors of hybrid nonlinear systems. I've constructed a new analytical construction of the transverse dynamics, not just the local transverse linearization, but transverse dynamics throughout the state space, which is going to be very important for this development. So I'll go through now bit of a description about what all that means. But before I get to that, I'll just motivate, apart from region of attraction analysis, this can also be used for control design on very complicated systems. So I'm going to go through this really quickly because Russ showed a bit of this before, but Little Dog is a bounding quadruped robot with 16-dimensional state space in the sagittal plane. It has 4 actuators. Dynamics are highly nonlinear, combinations of Euler-Lagrange type behavior and highly nonlinear spring, damper, ground contact, stick-slip interactions. So we computed the transverse linearization for this entire system, and we have stabilizing controllers here. So the red motion was Russ explained this. I think blue was nominal, green was controlled, and red was just running open loop for these bounding over rough terrain. So this stuff is useful for control design, but that's not what I'm talking about today. What is the transverse dynamics? Well, suppose a kind of section of our nominal motion. So this might be a motion which is computed using Cartier's methods, for example, or any other motion that you want to analyze is this red line here. And you want to define a set of planes around that. And these planes are going to be defined by this vector z here, which is a function of tau. Tau is your kind of index, phase index along this motion. So the transversal surfaces are these sets x, such that z transpose x minus x star being the point on the normal surface, equals 0. This is a definition of a hyperplane orthogonal to z. Having defined this locally, at least in some region around this red line, there's going to exist a mapping between your state x and 2 new coordinates, tau and x perp. So tau is going to be the, let's say, phase index. So given a state x in the whole state space, I'm going to find which of these surfaces I'm in, and that tau is this first coordinate. Then having found that surface, I've got a Euclidean coordinate system on that surface, which is of lower dimension. It's 1 less dimension because it's a hyperplane, and that's my x perp.
So this seems like it depends upon having a metric in order to be able to define perpendicularity. How do you get a metric, say, in a general phase space or general state space?
I'm going to discuss that. And in fact, we're not going to require that these transversal surfaces be orthogonal. For local analysis, orthogonal is great. But when you start going to regional analysis, there's reason to either, well, there's kind of an equivalence between sticking with the whatever metric you started with and searching over different z vectors here to choose the different transversal surfaces, or searching over a new Riemannian metric which has a different definition of orthogonality. That would be equivalent. But we find that for reasons of simplicity and numerical optimization, it's easier to search over these vectors than it is to search over a new Riemannian metric.
The reason I'm even troubled by the Riemannian metric, because if I go to a configuration space that's got finite angles, finite rotations, then I don't think you can find a metric.
Yeah. So I will.
So this is, I'm not criticizing.
Okay. There are special things you have to do to deal with things like switching surfaces, and we can deal with. I would say this is a bit like a switching surface. I haven't actually explicitly considered the case you're talking about, but we can discuss it later, I think. Yeah. Okay, so is this kind of clear? This is just a change of coordinates, which makes sense locally.
Z is tangent to that red line?
No, not necessarily. It can be, but it's not necessarily. I'm going to start with it tangent and then move to it being not tangent. So in these new coordinates, we can derive differential equations. So we have dynamics for x perp, and it might have some parts which are linear in x perp and the state, and some higher order terms. It's interesting to note, and this is a very important point, that the tau coordinate also has dynamics. So if you're familiar with Poincare map analysis, when you look at your Poincare map, you start somewhere off-center in the map, you run the solution around until it hits the Poincare surface again, just for a fixed Poincare map analysis. It's not going to have taken the same time as the nominal limit cycle to get back, right? And the intuition here is the same. If I start at a state off the nominal, I'm going to move through these transversal surfaces, but the time isn't going to be ticking forward as it was on the nominal. It's going to be going slower or faster depending on lots of things about the dynamics of the system and the geometry of these surfaces. But we've derived an explicit differential equation for how these dynamics evolve. If we look at just the linear part of this x perp dynamics, so you notice that this is kind of higher order terms in x perp and tau. So tau dot equals 1 locally if you are on the desired cycle, time is ticking forward as usual, but it can vary off that. And if we look at just the local behavior of the X-perp dynamics, this is called the transverse linearization. And intuitively what we want is, we don't really care what's happening with tau, it's going to tick forward however it wants to. We really want X-perp to be stable. And if X-perp goes to 0, then we're on our limit cycle.
Question?
Yeah.
So the statement you wanted X-perp to be stable, it's not clear to me. It may well be the case for reasonable controllers that portions of the limit cycle diverge locally.
That's fine.
So why do you then say X-perp should be stable?
But not necessarily, okay, stable over the entire cycle. So it can go away and come back again, and that will be, well, when I come to the description of the Lyapunov analysis, our Lyapunov function will kind of grow and contract at the same point.
Yeah, but a perfectly reasonable failure mode for a walker is to go faster, 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 and blow up in the
But that wouldn't be stable over like 1 footstep cycle. It can, within a phase, it can go away and come back. But
I'm just trying to figure out why this segregation of forwards and sideways makes sense. What?
Well, the tau is not necessarily even moving forwards. This extra high order nonlinear terms could go back behind 1, and that will actually happen on the rimless wheel, we'll see. So it could go backwards.
Looking at the section itself, I mean,
I'm trying to figure out why this rotation is a good idea.
Okay, well, we can either continue and hopefully it gets clearer,
My
or
conclusion is that we can't resolve this in the amount of time we have available.
okay, well, let's discuss it over lunch. Okay, so how do we certify stability over a region? What we're going to look for, and Anton hinted at this before as well, we're going to search for a Lyapunov function candidate, which is defined in X-perp but depends on tau. So it could be quadratic. It doesn't have to be quadratic, but the simplest classes of functions to search over are quadratic. So what I've illustrated here is kind of a nominal cycle, and this doesn't have any impacts, but this is just an illustration, and a bunch of these transversal surfaces around it. On one of these surfaces, characterized by a particular tau, there's this level set V is less than 1, which is X-perp transpose P of X is less than 1. So it's going to be an ellipsoid in this transversal coordinate system. And if we can come up with some possibly tau varying set of these ellipsoids and prove that in some region, some level set of V, the time derivative of this function is decreasing everywhere, then we've proven stability. This is probably many people in the audience will be familiar with Lyapunov analysis, but if you're not, this kind of argument just says that in these regions, our system is guaranteed to converge. So how do we check for a nonlinear system whether or not we have this V dot less than 0? And that's the way we do that is with what's known as the sums of squares relaxation. So I'll briefly describe what that is. And I'll describe it using a much simpler example. Suppose we had a single polynomial. So with its polynomial of a single variable, say this one here, and we wanted to check if everywhere of all x is this positive. This is a pretty hard problem. Okay, for even if you go for multivariate polynomials and you go for over regions, in fact it's actually NP hard to compute exactly. It's something that mathematicians have studied for a really long time, how to check this sort of thing. Semi-algebraic optimization is a big area. So what is a really powerful tool from that is what is called the sums of squares relaxation. Now it's a sufficient condition for this to be positive everywhere or non-negative everywhere, but it's not necessary, but it's very useful in practice. So I won't get you to go through the exercise, but if you take this matrix, which is a matrix in a vector of, we call them monomials, so it's 1x then x squared, and if it were a multivariate polynomial, we could add x times y, x squared times y, and so on, all the different combinations of these monomials, which make up a polynomial, and we construct a matrix of this form, you can multiply this out and see that it actually matches exactly this polynomial. And it turns out that this matrix here in the middle is positive definite, which means no matter what you substitute for x in here, this ends up being a positive number. So by this construction, we've proven that this is a positive polynomial. So in general, for a polynomial p of x, if one can find a matrix x such that in this vector of monomials, which is easy to construct, p equals m dash sm, then p of x is non-negative. And doing this search is actually, this is something Pablo Barillo, who we've been lucky enough to work with, has really developed a lot. This search is a semi-definite program, and this can be solved very efficiently using interior point methods, software like Sudumi, for example. So this is the basic way in which we check positivity of polynomial systems. And Russ mentioned as well, this also works for mixed trigonometric polynomial systems like mechanical systems. Often we'll just take a Taylor series approximation, but there are much more exact things you can do if you want. I'm going to kind of gloss over this quickly, but if you want to look at positivity over a region, you're not just checking positivity of the function itself, you're also searching for Lagrange multipliers, which are positive, and then the sum of the function and those Lagrange multipliers being, well, in this case it's negative, because I was looking for a decreasing Lyapunov function. But these Lagrange multipliers force negativity inside a region. And once again, you can search for these Lagrange multipliers efficiently. So, to take an example of how all this works in practice, the van der Pol oscillator is probably one of the simplest dynamical systems which actually exhibits stable limit cycle behavior. So this blue line here is the limit cycle of this differential equation, y and y dot, that is here. This differential equation has a single equilibrium, an unstable equilibrium at the origin, and from everywhere else in the phase space, every other point in the phase space converges to this. So and this is kind of well known as well studied, so we thought this is a good, simple system to test our methods on. So if we go ahead and compute using all this kind of theory, which I've kind of glossed over, but there it is. If we compute a candidate Lyapunov function using the Lyapunov differential equation from the transverse linearization, which is kind of the first thing any control theorist would do, and using orthogonal transversal surfaces, this is the region of attraction that comes out of our optimization process. Now, this is obviously not proving this almost global stability property, which I've just said the van der Pol oscillator has. And the limiting points are actually these points here, and maybe it's coming up against it here. And this is because we've chosen that the transversal surfaces should be orthogonal to the limit cycle. And what this means is beyond these, or at these points, or beyond these points, this local change of coordinates to x perp and tau is no longer well defined. If you look at the dynamical equation I derived for tau dot at these points, you get a singularity there. So this is kind of a, this is not saying that the system isn't orbitally stable from outside this point. It's a limitation of this construction of transversal surfaces. But for this particular example, we know what a good set of transversal surfaces would be. We could pick them centered at the origin and just kind of radiating out from the origin. And that's not going to have any problems with these singularities. That's something we could kind of cheat with here. But if we do that and still just use the candidate Lyapunov function that you get from the linear theory, it doesn't improve things much. We don't have these points of singularity, but we've still got pretty narrow regions in which we're proving orbital stability. And it actually helps a lot to do your optimization both over the Lagrange multipliers, which verify stability, and over the Lyapunov function itself. So whilst this quadratic Lyapunov function is great for the linear theory, it's not optimal for regional analysis. So we're going to do an optimization in that as well, and that's also can be done very efficiently. I'm searching here over quadratic Lyapunov functions in quite a general form, and this is the regions I get now. So it's pushed in right to the middle. There's a little couple of gaps missing there just because of the degrees of the polynomials I was searching over. And you see that it's pushed out into kind of free space about this much. And the reason it got stuck there is because a quadratic Lyapunov function has to be symmetric around the limit cycle. So it can push in until it hits the unstable fixed point, and there the conditions for orbital stability will break, and that limits how far it can push out. We're looking at using higher order polynomials for Lyapunov functions, but this is kind of quite recent results, so this is all work in progress. But we think with higher order Lyapunov functions, we might be able to push this sort of thing out. If we move now to an example which is a bit closer to...
We're going to leave for coffee break in 5 minutes.
All right. I'll push through it pretty quickly then. All right, I'm almost done. If we look at an example which is a bit closer to what people are doing here, the rimless wheel, this is, once again, just a planar system, very simple, with known regions of attraction. So for the parameters we chose here, this kind of salmon-colored area with the regions of attraction, the blue line is the limit cycle. These green lines are the homoclinic orbits of this inverted pendulum type dynamics. And if I just run my algorithms on this, I get regions of attraction like this. Now, once again, we're kind of limited by the fact that it's pushing up against the line here, so a quadratic Lyapunov function is symmetric around these points. And we notice that in this case, I should mention that for hybrid limit cycles with switching surfaces, for the analysis to make sense, you're going to want your transversal surfaces to line up with your switching surfaces. And that allows everything to pass through naturally. And for the rimless wheel, it's really easy to have that happen with just vertical transversal surfaces. And that also avoids any problem of any singularities, because they're all parallel. So this is kind of a really easy example where everything works out nicely. And I should also thank Michael Levashov, who did the computation for this example. When we come to more general systems, for example, the regions I showed for the compass gate, just vertical slices isn't going to work. We have to line up with the transversal surfaces. So we have to do actually a trajectory optimization in Z. And this is using exactly the same techniques that Manoj presented in his tutorial. So we're going to start with an initial guess that we're going to have orthogonal transversal surfaces, but we know that's probably not right. And we're going to search locally over some function parameterization, like splines, minimizing the maximum value of this curvature-like function. And it's a bit like curvature, because what it defines, for these z's being parallel transported along the orbit, the closest point in the state space at which a singularity could occur. So we're going to push that out as far as we can. And then we also have a constraint that z be normal to switching surfaces. So that means our transversal surfaces line up at the impact points. And that was how we computed the compass gate. This is my second last slide. I will mention for kind of future work, there are very deep and very natural connections between the Lyapunov analysis that we're doing here and robustness analysis via nonlinear extensions of H-infinity integral quadratic constraints. So instead of searching for Lyapunov functions, we're searching for storage functions that verify interconnections of various system components are going to be stable. That could be time delays, that could be energy-bounded uncertain elements, infinite dimensional elements, and so on. So this is Andy and Rumsfeld's known unknowns.
The known unknowns is just his.
Oh, that's just his?
My
All right.
calculation is the unknown unknowns.
Okay, so we don't have them in our computational framework yet, but maybe you can tell us how to do that.
I don't know about them.
Yeah, exactly. So it's hard to compute them analytically. All right, but this, the kind of thing we'd like to prove with this is for an uncertain system model, possibly with disturbances and time delays in the feedback controller, that we probably can't get convergence to the nominal limit cycle, but in some tube around that, which still looks like a qualitative walking-like motion, still goes through all the regions of state space we want, we're guaranteeing convergence to that tube. A kind of practical stability is how control people talk about that. So that's it. Time for coffee, I guess. What I've presented is a new method for computing regions of stability for limit cycles of nonlinear hybrid systems. The whole method is based on efficient computation of Lyapunov functions and verification of Lyapunov functions over regions using semi-definite programming. The same techniques are also very useful for control design, and they end up in a state feedback controller, not a time-varying controller, because this tau is a phase variable, which is actually one of your state variables. So that's kind of fits with that ideological bias as well. And there's very deep connections to classical robustness analysis, which we're working on now with Alex Magretsky.
Yeah, I'm going to claim the one question, and then I'll
All right.
announce the copy. But let's say somebody wanted to implement this, and they didn't really care at all about the theory, understanding it, or anything about it.
We're working on a toolbox, so
Yes. How
Yeah.
difficult would it be to learn and use?
if they've ever done things like LMI analysis or used
They
them,
haven't
done
don't
any.
know what LMI
So,
stands for.
all right. Then the easiest thing to do would be wait, hopefully, a couple of months or something until we release the toolbox where everything will be done, and you're going to be giving a trajectory and a nonlinear system and defining where your switching surfaces are, and we'll compute regions. We're working on that now. The examples you saw here were a bit kind of hacked together for those specific examples, but we're trying to make it all general. This is really just a few weeks old results, so it's coming. It's coming.
But no written resource anywhere? Written?
Some of it. There's a recent paper in IJRR which is doing the sums of squares verification stuff, but not for the limit cycles and not for the switching surfaces, not for the hybrid dynamics. I'm actually writing a paper on what you've seen today here now, and it's not even submitted anywhere yet. So it'll come, but it's not out yet.
Maybe an intermediate step would be you should send us your model. Maybe in a month, send us
Yeah.
your model.
If anybody has a model they really want to analyze stability of,
And you don't have to know what LMI means.
yeah, we can have a look at it.